computational aspects of, in theory, the computational aspects of computing second fundamental form, first fundamental form, principal curvatures, mean curvature, Gauss curvature. Okay, so let's start today with a couple of examples just to get a bit of practice. Okay, as I said, this is typically the way you apply the theory of surfaces also in practical problems. So it's better to be. But as you will see, it's quite easy. I mean, the computational aspect of this theory is quite simple. So let's start with, the simplest class of surfaces is always graphs. Okay, so here actually, I know, students always want homeworks, examples. Here you have an infinite class of examples you can do by yourself. Take any function and compute the graph and compute everything you want to compute. Okay, so let's take the graph. Actually, just to complicate things a bit. But this is, if you write it as an equation, but if the equation starts like z equal to something, that's automatically a graph, no? Because the function that you are looking is what? So this is gamma of f, where f now is a function from the whole of R2. The domain of the function is clearly, there are no problems here, to R, and f of uv, so it's already written in the coordinates we use for charts, is 1/2 u squared plus v squared. Okay, that's clear. So, okay, so we have a chart. Remember, in fact, the delicate problem usually, even in computation, is to have charts, construct charts. If your surface is born not like this, then the problem could be building charts by hand. Okay? But if you have a chart immediately, remember, in the case of a graph, this means that this is covered by one chart where the domain is R2 and x of uv is simply uv f of uv. Okay, so once you have this, then everything becomes. So in fact, my suggestion, instead of computing each coefficient of every matrix, so remember the theory tells you, now that you have a chart, you have a standard basis of the tangent space. Now, with respect to this basis, remember that everything is with respect to a basis. It's not something, one thing is linear operators or quadratic forms and so on, intrinsically, and then once you have a basis, you write down a matrix. So a linear map is not a matrix, okay? It's different. That's just the representation with respect to the basis. But here we have a standard basis, which is xu, xv, every time you have a chart. So with respect to this basis, you should compute all these matrices, the three matrices, no? First fundamental form, second fundamental form, and D actually in order, first fundamental form minus DMP, no? Minus the differential of the Gauss map, and then the second fundamental form, which is essentially the composition of the first two with one inverse. Now, instead of doing this, you know already, if you look back to your notes, that what you really need is the vectors of the partial derivatives, xu and xv, the normal vector, and then the vectors of the second derivatives. So I propose to compute first all the vectors that you need, and then do the computation afterwards. Okay? So let's start. So without thinking, what I'm saying is that this is a moment where you switch off your brain and you do something. Okay? The something is, write down the vectors that we will need. So this is, of course, 1, 0, u. And actually, I also propose to write them in column because your colleague is not here, but I will never use my hand. Okay? I will have to compute minors, so I prefer to have them. I know there is space there, but I won't use it. Okay? Actually, out of this, I can compute immediately n. Okay, so that's a good way to use this space. And now, so n will be what? Will be the vector product normalized. Well, plus or minus. And remember here the ambiguity. I mean, this would, technically speaking, in your notes, this would be nx, because I'm writing it as a function of uv. Okay, but we have identified the surface with the domain of the chart, so I call it n. It's the same vector, it's just a different domain. So n is what? It's v, it's, well, minus u, minus v, 1, normalized. So, okay. And then I know that I will need xuu, which is 0, 0, 1, xuv, which is 0, 0, 0. Of course, every time you get a vector equal to 0, you open a bottle of something, okay? Because that means many coefficients will be 0 automatically at the end. xvv will be 0, 0, 1 again. So everything is quite simple here. So now I have everything on the blackboard. So now I know I can start computing the coefficients of the first fundamental form. Let's go in order. These were the capital letters, no? And E is what? Is the norm squared of the first. I mean, you have to choose which is your first. Okay. So let's say U comes before V. So xu, so this is clearly U plus U squared. F is the scalar product of the two, so it's uv, and G is 1 plus V squared. Of course, everything is symmetric in U and V, so I could even not do the computation. Then I start computing the coefficients of minus D and P. So little e, now this time I write what it is, because this would be minus nu xu. Remember, you have two formulae now to choose. It's minus nu xu, or it's n xuu. And actually, I usually prefer this one because I hate differentiating square roots. Okay? So this is n xuu. Of course, this takes care only of the third component, so it's 1 over square root. In fact, let's write, just to save blackboard, it's 1 plus u squared plus v squared to minus 1/2. Okay? What is little f? Little f will be n xuv, and now that's where the bottle comes. And G is, of course, symmetric, so it has to be the same. It is actually the same vector. So it's 1 plus u squared plus v squared to the minus 1/2. Okay. Now you have two options, because okay, this would be these are the matrix coefficients. Remember that out of this you build the two symmetric matrices. So the first fundamental form, which is represented with respect to this basis by EFFG, and minus DMP, which is represented with respect to this basis by EFFG. Now, strictly speaking, if you need to know principal curvature, Gauss curvature, and so on, the way we define, if you follow the definitions, I should write down the matrix representation of 2P. Oh, well, of course, this is at the point P. And remember, this is what we call the A11, A12, with this kind of ugly formula, no? So that would be this times this inverse, no? Now,
actually, the second form is EFFG.
Second form is EFFG. So minus DM.
Minus DM.
mm-hmm. You're right. Okay? So, but strictly speaking, I should, if I want to know right now which are the principal curvature, I should diagonalize this matrix. Okay? Which is quite horrible to do it. So I instead prefer to compute mean curvature and Gauss curvature with the formula we got, and then reconstruct K1, K2. Okay? It's computationally easier. I mean, I try to minimize computational mistakes. So of course, the easy one, I mean, to remember, is the Gauss curvature. I mean, so what I'm saying is that I will almost never compute actually this. Okay? Because just with these, which have you seen is very simple, I can compute so this is the magic formula, and now, okay, it's EG minus F squared, so it's 1 plus U squared plus V squared to the minus 1 divided by EG minus F squared. 1 plus U squared times 1 plus V squared minus U squared V squared. Okay? Okay, and now just the magic happens. I mean, of course, here there is a cancellation, and you can see what is left here is exactly this one. So this is just 1 plus U squared plus V squared to the minus 2. Okay? Anyway, whatever that is, that's, so finally, I mean, a genuine function, no? I mean, not a constant, not 1 over R, not 0. Okay, so this depends point by point. I mean, of course, you can start making considerations of the form, well, okay, it's a function, but it's always positive, for example. I mean, let's start getting a little bit of feeling, because that's what we are going to discuss next in the theory. What does it mean, for example, for this function to be positive or negative, or so? Okay, so it's a positive function. Actually, if you really want to get a feeling, you should also draw the surface, so just to understand where the Gauss curvature does something. So, you know what kind of surface that is? I mean, are you able to draw it without asking your Google drawing app? No? I mean, it's quite easy, because this is of course looks like a circle, no? I mean, if it was in the plane, this is a circle of radius 1. But then that means it's a circle in the xy plane moving around the space with radius z. So of course, first of all, for z negative, I get nothing, no? Because x squared, so below the z equal to 0 plane, there is nothing. And z equal to 0 starts something. I mean, this suggests to think of this, to understand this surface, I mean, in general, all these type of surfaces, all surfaces given by quadratic equations, the best way to understand them is to slice them. Now, because in theory, you should be able to recognize immediately what kind of conic a plane curve of degree 2 is. It's a parabola, it's an hyperbola, it's an ellipse, it's a pair of lines. So this, just by looking at the quadratic equation in 2 variables, you should be able to understand. So when there are 3 variables, the idea is, of course, to go back to 2 variables by slicing. Okay, so you slice. So of course, for z equal to 0, you get 1 point. So, and then as z increases, this becomes circles of radius, well, square root of 2 times z. So whatever that is, I mean, of course, since I'm not drawing the unit of measure, this looks like this. No? These are circles of radius which is increasing as z goes up. Okay? Of course, this is called what? A paraboloid, a one-sheet paraboloid. Okay? So that's the picture. So now that you have the function, the Gauss curvature function, you can draw all the, I mean, you can think of what's going on. For example, for UV, this becomes the UV plane, no? Because that's where you are writing as a graph. So in the UV plane, for example, what else can you say? This is a positive function, but it's also going to 0 as UV goes to infinity, no? So that means this is becoming flatter and flatter when you go away from the bulk of the surface, okay? And in fact, the maximal point of this function is here. No? This is the most curved point of the surface, for example. I mean, these are just considerations. I mean, you give me a function and you want to understand a little bit how it looks compared to the picture, no? And then, of course, the other interesting thing you can notice, I mean, in principle, I should have gotten a function of 3, well, of 2, but I mean, where is z here? No, I mean, every time you fix z, you get the same number. No, because z is u squared plus v squared divided by 2. Okay? So on every horizontal plane, every point on the same horizontal plane have the same Gauss curvature, which actually fits with the fact that this surface is kind of rotational invariant. I mean, you are not able to distinguish. This point here and this point here are actually the same, geometrically speaking, because just rotate everything and nothing has changed. Okay? But anyway, so these are just the type of consideration we will have to do on a surface in general, so that's why I'm starting practicing. But now, if the idea was compute, then the second step is, of course, mean curvature. And mean curvature, I have no. Okay, it's 1/2 EG plus GE minus 2FF, if I remember the formula you have in your notes. Okay, I don't remember it, but then you plug in all these things, you compute it, and actually just for the pleasure of writing the result, this is just, you should get this. It's 2 plus u squared plus v squared, 1 plus u squared plus v squared, 3/2. Okay? Again, here, this again, you can interpret it in the same way. I mean, you can make the same kind of considerations. But now remember that, for example, when you start saying, I noticed that this is a positive function, remember that this depends on the choice of n. Okay? So being positive is not something God-given. It depends on the fact that I've chosen this. So if you want to start making interpretation of this fact, you also have to draw, and actually, how do I recognize this? Because of course, if I pick a point, I draw the tangent space, I have the two normal vectors like this, no? So which one did I pick? I picked the one with positive z. I mean, that's the way I recognize it, no? Because z will always be 1 divided by something, no? Imagine that you are actually, if you are doing it here, which one did I pick? 0, 0, 1. So I decided to take the normal vector, this normal vector here. The one going sometimes inside, if you want to think of the inside of the surface, okay? So with respect to this orientation, the mean curvature becomes positive. Okay, and then it has similar properties. It becomes goes to 0 as uv go to infinity. No? Okay, that's it. I mean, we will see if this has some kind of intergeometric interpretation. Okay, now out of this, I should, typically the problem actually is about principal curvatures. Now, if the question is just about, if you just need principal curvature, meaning the actual functions, k1 of p, k2 of p, I don't need to diagonalize, as I said, because I can take the formula, what is h plus, well, I guess this is h minus, no? Square root of h squared minus k. Yeah. Okay, so this is a way to recognize k1 and k2, and I just plugged in this object, these functions, and I compute them. A bit more subtle if the question is about computing the principal directions, because then there is no escape. I really have to compute, to diagonalize, because now these would be the eigenvalues, but now I need to understand which are the eigenvectors corresponding to this and this. And then I really have to do the linear algebra. And this typically it's a bit heavy, but I mean, I'm not going to do it because it's just there. I mean, finding the eigenvectors of a 2 by 2 matrix, okay? That's it, with the complicated. Okay, any questions? Because unfortunately I have to erase everything to go to example 2. Is it okay? Now, example 2. let's start doing some, so it's again an excuse to put in our bag another beautiful surface. So this time, I mean, this is really one of the most famous surfaces, so with the excuse of... okay, let me write down the chart for this surface, and then we will comment on what it means. So take, again, UV, now our parameters, I mean, there are no constraints on U and V, okay? And take this this parameterization here. So in fact, and I'll also pick R, but I don't want it to be 0. So do we all agree that the asterisk means non-zero? Okay. So V cos U, V sin U, AU. Okay. Okay, so where do we want to start? From the computations or for how it looks? Well, let's do the computations. I mean, okay, suppose I give you this is a chart of a surface. Okay, of course the first thing would be to prove that this is actually a chart. Okay, you do it. I mean, in fact, actually, when you do the computation, you really have to prove in some sense, because remember, I mean, modulo all the stupid things, set theoretic, smoothness, and so on. But the delicate thing is always to prove that the rank of dx is equal to 2. Or the differential of the map x is maximal. But this is something we will see in the computations, because how do you check it? You compute xu, you compute xv, and one of the equivalent way to say that the rank is maximal is to compute the vector product and check if it's not 0. But that would be actually my candidate normal vector. So if it becomes 0, I understand, I see it in the computations. So let's do it. So again, xu xv xuu xuv and xvv. Okay, this I do it without even thinking. Another bottle, okay? And now n. And in fact, even if you feel not particularly smart, you understand why. Okay, to write them using the same space, so that n becomes minus a sin u a cos u minus v squared minus v cos squared, so it's minus v. Okay, and then again I have to normalize it. Okay, so this is become divided by okay. Actually, this is the moment where I understand that I'm on the maximal rank condition, because you see this is never 0, because whatever this is always is always a positive, strictly positive function. Okay, so the differential of x is always of maximal rank. Okay, that's the moment I understand it. Okay, so now again, let's compute first fundamental form, second fundamental form, and DNG, and everything. So these are the easy one. The capitals are, of course, just the scalar product of the first with itself. So it's v squared plus a squared. Good. 1. So g is equal to 1. Okay, so I got two constants for free. Okay. Now little e is this times this. That's a bit less. Let's see. It's plus av sine cos minus av sine cos 0. Lucky. Okay. Then f is plus a sine squared plus a cos squared plus 0. Well, I was very lucky. Okay. Well, I was very lucky because somebody gave me a nice parameterization, of course. But I mean, now Gauss curvature Eg minus f squared. Okay. Divided by Eg minus f squared. Okay. So this time, for example, it's become negative everywhere, plus considerations that we will do when we will be able to draw the picture. And mean curvature, 1/2 E plus GG minus 2FF. Actually, I'm starting remembering. I'm getting worried. I mean, we should stop doing it. It's actually not too hard to remember, but it's EG plus EG minus 2FF. I mean, it's basically the only way to mix all these letters, okay? Divided by something. And now I don't even have to do the computation because I don't start but in any case, EG minus GG, and you check immediately that this becomes equal to 0. Okay? It's too famous to do it again. So, okay. So, okay. So, and actually, so here all the considerations. 0 is the only number which is, of course, invariant by changing sign. So, whatever the orientation was, this would be 0. So now the question is, what kind of surface is it? Okay. Can we understand a little bit geometrically? How does it look? After all, it's made of very simple functions. So, well, of course, when you see something like this, where the variables are so nicely decoupled, no, it's good to, maybe this time, maybe it's not really slicing a good idea. I mean, if I slice, for example, with z equal to a constant, that means basically u equal to a is a fixed parameter. You can think of a is equal to 50, okay? So if I take z equal to something, it's like saying u is equal to a fixed thing. Well, you can also do it in that way, but I think it's much easier to think of, fix, for example, if you fix v and you let u move, what's going on, and vice versa. If you fix v and if you fix u and let v move, what do you get? So basically, by reducing the problem to describe two curves, because of course if I fix one, I have only one parameter moving, so I have a curve. Okay. So let's try to draw a picture. Okay. What is simpler? What do you choose? Which one do you want to fix first?
You.
It's 50-50. Okay, so let's fix V. Let's fix V for the moment. So suppose V, I mean, now in your head, I mean, let's call it V naught, but in your head, think it's 1. Okay. And now U is going from minus infinity to plus infinity. Which curve should I draw? is the helix of kind of base A. Okay, so basically what this means is that if I fix V, and actually I even know what does it mean V. So in some sense now I can even do, in any case, what is V? V is equal to V naught. It's kind of the radius of the helix, no? So it's always for any V I get an helix, but when I V varies, the helix is going up or down, okay? So that's one way to think of it. So let's say I start drawing an helix, going, let's say for example A, well, it doesn't matter, let's say A is positive. Okay, so this curve certainly lies on this surface. Okay, now let's play the opposite game. Now I fix U and V is moving. So that geometrically that means I picked one point of this helix because I fix U. And now, which was given, this, suppose that this helix is given by some choice of V is equal to V naught. Okay, so I fix this V naught and I draw this helix. Now I pick one point over this helix, so now I fix U equal to U naught. And now V starts moving again. Okay, so this would be actually the point X of U naught V naught. Okay, but now U naught stays there and V naught moves. How does it move? Well, linearly. Okay, so what is it doing? V is just describing, so the curve alpha, no, alpha of V given by this sine U, cos U0, sine U0, U0 times V in this way gives me what?
Direction. It's moving.
Which direction? I mean, okay, it's a line. Okay, we have to decide where to put this straight line. It's clearly a straight line passing through this point for sure, but I still need a vector. So is this line, is which line? This line here would have V also here.
No, from 0 to 8.
Exactly. Exactly. You see, the directional vector of this line, of the V line, is horizontal. Okay, it does not have a Z component. So it is the one given by, if you take this vector, but you kill the third component, so it's this. Okay? Okay, so now geometrically I have a very clear picture. My picture will be horrible at the end, but in your mind it's very clear. So it's an helix, and now for every point of the helix, you draw the straight line orthogonal to the z-axis. Okay, passing through this point. So you start covering this surface with lines. Okay, so now you can reverse the process. You can imagine that this is a straight line which starts moving up and rotates, no? I mean, points rotate on it, it's kind of the whole line is moving like a helix, okay? When it moves up or down. Up or down depends on A, positive or negative, of course, okay? So, we actually live with this surface in our buildings. In fact, this is the moment where even the screwdriver, no? I mean, we use this surface every day. So this is, of course, a famous surface. The curve is called the helix. Without much fantasy, this is called the helicoid. Okay? And it's the one that architects use to build the staircase.
Yeah.
No? So, of course, when you build a staircase, typically you kill what is inside the cylinder. You take just a piece. No? There is a hole, usually, in between, and there is this piece of helicoid going that they use for constructions. Okay, I think at the end of March you will have a couple of lectures specifically devoted to surfaces which satisfy this property, because this is one of the most beautiful property, not just of surfaces, of sets. Okay? It's one of the most richest part of geometry and analysis. Okay? This is called a minimal surface. Okay? It's one of the simple examples. Of course, you know another one with this property. You know the plane. So the plane is a minimal surface. The helicoid is a minimal surface. There are many others, but actually, how many? It's a very active field of research. Okay, depending on problem. And the word minimal, just to satisfy for the moment your curiosity, is there because this is the shape. This has this fantastic property. If you take a sufficiently small piece of this surface, you can actually build it in lab. I mean, in fact, in principle, you should be able to build the whole surface in a lab. But if you take a sufficiently small and you pick a wire, so basically what I'm saying, pick a domain over this surface. I mean, speaking mathematically. You pick a domain, but not of R3, of this surface here, and you take the boundary. So the boundary would be a curve. Okay? So this would be kind of a strange circle, I mean, twisted, deformed circle, put in space. Suppose you have it. You actually, I mean, you can build it. Now put it in soap and pull it up. Okay? Soap will take exactly the shape of the helicoid, which was in between. Okay? So this is the equation that nature uses to minimize area, which, if you believe some kind of metaphysical principle, is the same thing of minimizing energy of, I mean, why soap? I mean, soap is used many times in mathematics, but it's just a psychological thing. I mean, of course, there are also people using it, but we don't care as mathematicians. Soap is just a way to say nature wants to do the least effort to do something. So you want to use, soap knows for some reason that, so there is a psychology of soap. Soap wants to use the least possible soap to span the same curve. Okay? You want to minimize, this is a famous philosophical principle actually of nature. Okay? So you're minimizing energy, effort in doing whatever you do. Okay? It's a principle that has never been contradicted up to now. I mean, it's the principle which explains why, I mean, if you drop a ball, why it falls vertically to the floor. I mean, why this ball doesn't start going.
Because the action would be minimized over this path.
And why? So the fact that you minimize the action works. Why? Somebody could, a philosopher could ask you why. I mean, that's the way we work, but I mean, it's not something for free. Okay? And that here it comes again. I mean, soap or whatever. So there is a kind of an energy here, which is the quantity, which is kind of comparable to the area. In this case, because quantity of soap is comparable to how much area this is. Okay? So basically the mathematical question is, which is the least area surface spanning a given curve in R3? This is this is called the Plateau Problem. Okay? And minimal surfaces are solutions to the Plateau Problem. Okay? So the helicoid is one.
So we are asking which surfaces having their boundary containing minimal area? Or?
No, if the Plateau Problem is kind of the version with boundary. So remember, the helicoid is, or the plane, these are surfaces which have no boundary.
Yes.
So to go back to the Plateau Problem, you have to choose the boundary on the surface. So the Plateau Problem just asks, take a closed curve in R3 and minimize the area among all surfaces which have this boundary. Okay? the solutions of if the solution exists, the solution will satisfy this equation. Okay? Good. That's one part of the story. Now, the other way around. I constructed geometrically, by accident if you want, just by beauty, a surface, a global surface, which actually everywhere satisfies this. So where is the plateau problem? Here there is no boundary. So basically I have to play the game I was telling you. Now, this means that if I take a curve on this surface and I use it to set the plateau problem, as a solution I will find the piece of the surface. Okay? It's the same, I mean, think of the plane. I mean, here maybe pictures are becoming a bit twisted, but I mean, in some you can say the plane is a minimal surface. But of course, you cannot put in the SOAP an infinite plane. So what do? The point is, every time you take a planar curve, if you put it in SOAP, you can bet it. Even my kids know it. The solution is what? Where does the SOAP? I mean, the SOAP becomes planar. And why is that? What? The mathematical explanation, because the plane has zero mean curvature. Okay? Now I've made it a bit rough. I mean, there are subtleties in all this story, but depending on how big is this size, you could have more than one solution. Okay, but okay, this is a very, very big theory. One of the most beautiful theory, I think, in mathematics, okay? Independently of SOAP. I mean, this is really ground zero for mathematicians, okay? So, you will have 2 lectures specifically on this, okay? On the theory of minimal surfaces. It's beautiful because I think every branch of mathematics comes into the game. I mean, there is a beautiful interaction between this equation and holomorphic functions, a very classical thing. There are beautiful interactions between this equation and algebraic geometry. I mean, basically, every branch of mathematics has given contribution to the theory of minimal surface. And vice versa, the problems coming from minimal surfaces have motivated questions in almost every branch of mathematics, and theoretical physics, actually. Yeah? If you ask a physicist what is a string, and what are branes, which is the language of string theory, that's the answer. Okay? So they are everywhere. Because they are the prototype of the simplest variational problem in dimension 2. That's basically the idea. You see, variational problems are for sure crucial. Now in dimension 1, the most natural variational problem would be actually this would be the 2-dimensional analog of which question in dimension 1. That's always a good exercise I would like you to practice. Every question exists in every dimension. Maybe sometimes in some dimension it's trivial, so you discard it very quickly. But when you ask a question in dimension 3, 4, 5, whatever, there should be an analog question in lower and higher dimensions that maybe can help. For some reason, maybe in dimension 1 it's simple, and this gives you some feeling. So fixing the boundary and minimizing the area inside is what? Well, you have to think, boundary is dimension 1, and I'm looking for an object of dimension 2, which minimizes area. So if I reduce by 1 all dimensions, I'm saying boundary dimension 0, and I'm looking for an object of dimension 1. Now, typically the area of an object of dimension 1 is not called area, it's called length. So now this is the 2-dimensional version of which problem? Give me a 0-dimensional boundary. So give me points. And you are asking me which is the curve of shortest length which connects these points. In fact, it's a beautiful problem by itself. Okay? By no means trivial, depending in fact on how many points, where they are put. Okay? Of course, we know much more about the problem about points and curves. It's easier. It's easier than the 2-dimensional, the 3-dimensional, and so on. But still, it's not a trivial question. Because of course now as you can see, I mean, my attitude is by purely theoretical things, but then you can imagine there are all the computational aspects. No? These things actually are useful in nature. The problem of connecting points by curves of shortest length is actually what people use, I mean, what engineers use to construct tubes, no? I mean, undergrounds. I mean, why people, I mean, this is not, I mean, I like it because I like it. I don't have to justify it to anybody. I'm proud to be a mathematician. But in this case, I mean, there is absolutely no problem in motivating, no? I mean, this could be the stops of a tube, no, of an underground in a town, and the question is, where should I dig the underground, making the least effort to connect all these places? Okay, so I mean, this is, and if you really, and then of course the answer of a mathematician would be, there exists a solution in the Holder space. The engineers wants to dig the underground. So I mean, there are also the computational problems, okay, involved in this, which are beautiful actually. There are numerical problems, computer type approaches, and so on. Okay, this was just entertainment. If you are tired in the evenings, Google minimal surfaces and you can see libraries of pictures on minimal surfaces. Okay, now we have to, and I hope I convinced with these examples that the computational side, as long as, I have to confess, there is a little bit of cheating, as long as you are not, you don't care about principal directions, okay? If the question avoids principal directions, computations are very easy. If the question involves computing the eigenvectors, unfortunately this takes another 20 minutes for every example, because you really have to compute the eigenvectors. Okay? But that's it. Now let's move on in the theory. And now, actually the jump comes from you see, we worked a bit, not too much, about 15 minutes to construct the differential of a map between two surfaces. Actually, we didn't work too much because we worked before. We gave a definition of differential of a map from Rn to Rk, which was actually importable to anywhere. Okay. Now, if you think, now we have to, the next step is, of course, when you give me a function. So this was enough to speak about differentiability of functions, of course, but for example, about critical points. But I mean, we want to do calculus. Calculus is what? Give me a functions. You want to know, give me a function over some domain. I want to know minima, maximum, saddle points. Okay? How do I recognize minimum, maximum, saddle point in calculus? Well, of course, but how do I distinguish a minimum from a maximum? Second derivative. So where is the second derivative now? So up to now we are able to do first derivatives. Okay? So this is enough to say regular value, non-regular value, and so on. But if I want to distinguish between what kind of critical point something is, I need to have a notion of second derivative. And that's exactly what we are going to do now. Okay? So now, and of course, the object will be called a Hessian, as it is in calculus. So now the problem is how to define the Hessian of a function defined over a surface. Now the problem is, of course, this we will define at the point, and then of course, but this point, as we will see, okay, we need also to have a function, f from s to r, so a real valued function. We pick a point, and now we assume P critical for f. So our definition for f will be good only under this. So I will not be able to compute deviation anywhere, okay, but only at critical points. So first, so think in practice what we will do. We take a function, we look for critical points by looking at the differential. At those points, in order to distinguish what kind of critical points they are, I compute deviation. But I won't be able to compute deviation everywhere, at least with what I'm going to say
So
now.
S here is a surface or just a domain in R?
S, no, S is a regular surface.
Okay.
I will not say again. I mean, in my curves, in these lectures, S is a regular surface. Okay? So now, so this is a big definition, okay? Under these conventions, I will denote by D2F, I mean, at the point P. So this is what I will call the Hessian of the function at the point P. To be what? Well, in principle, I could define it a bit more generally, but I don't care. So it's something which takes one vector, one tangent vector at this point, and gives me a number. How? Well, maybe this is not very comfortable for you at the moment. I mean, the Hessian, whatever it was in calculus, even if you are thinking of it as a matrix, now I don't get angry, but I mean, because in calculus, you do calculus under the working condition that you always choose the standard basis of Rn. So now I'm defining the operator, but if it's a matrix, it means it takes two vectors and gives me something. So how come here I'm taking only one? And basically the idea is because I'm taking twice the same vector. If you want to go back, that's what I'm telling you, just because if you want to connect it with your old story. So I take a vector, and then of course I have an obvious candidate. If this is a tangent vector, there exists a curve alpha passing through P with velocity V. And now, of course, the differential was the first derivative. Why not looking at the second derivative, the acceleration of this curve? Why not? Okay? So of course, under the usual assumptions, alpha of 0 is equal to P, alpha prime of 0 is equal to V. Okay? Okay, so we face the same problem we had every time. Well defined, I mean, does this depend on alpha? Well, of course, we also, and then what does it really measure? I mean, is this going to answer the problem we wanted to solve? Okay, so first of all, let's give it a name. Okay. And now, let's prove immediately the key proposition. Okay? Under these assumptions, so of course, here this is meant always to be differential. I mean, of course, you need it to be at least C2 now, because otherwise I cannot take the second derivative. So D2FP deviation at the point is well defined. Meaning what? It does not depend on alpha. It depends only on P and V. Okay? Moreover, 1, it is a quadratic form. I will comment a little bit on really what it means on TPS. And then it answers, I mean, let's put everything in the same proposition. And it answers the problem for which we wrote it. So it is able to distinguish minimum, maximum, other type of critical points. In particular, so the calculus theorem holds, I could say, but let's elaborate a little bit what it means. If P is a local maximum for F, of course, I mean, I don't even write it, then the Hessian, so at the maximum, the Hessian has to be, well, semi-definite negative. Okay, be careful. This is this annoying problem of zero. Okay, is semi-definite negative. And actually, just to save a little bit of blackboard, because this is really the calculus theorem, no? So if it's a local maximum, then this is semi-definite. If it's a local minimum, this is semi-definite positive, okay? And the vice versa holds only under strong. So strong positive, strong negative imply, okay? For example, if for the vice versa, you have to impose is definite negative, then P is a local maximum. And of course, there is an analog statement. If it's definite positive, this is a local minimum. Okay? So there is always the indeterminate situation where it's semi-definite. If you know if it's semi-definite something, you cannot conclude that this is a local maximum or minimum. Okay? Okay, so this is the calculus theory. All right. So let's prove it, because you prove everything in one shot, as usual, because the idea is always the same. Write it down what it is, and hope there is a magic formula, doesn't matter how horrible it is, which on the left has your object, and on the left has this, and on the right has something where alpha magically disappeared. Okay? So, let's do it. As usual, so from now, in all these theorems, UX local chart. Around P. And of course, let's give names to everything. Remember, I don't even, now I stop drawing the picture. So P is a point on the surface. It comes from one point in U. So let's call it Q. So Q, X of Q is equal to P, okay? And Q will be given by a pair of coordinates AB. No, this would be a point in the plane, so it has to. Okay, so and as usual, by choosing epsilon sufficiently small, we can assume that alpha was a curve defined from minus epsilon to S, okay? So if it's in S, if epsilon is sufficiently small, alpha of its domain is contained in X of U, because topology, okay? It's an open set, so it has to be there. And then, as usual, I take, so now that alpha is a curve contained in this little piece of the surface, I can pull it back to the domain U by X inverse. And I take this curve beta to be X inverse composed alpha. I mean, up to now, this is actually always the same beginning of the proof as for the differential, for everything we did. Okay? And as usual, beta of t, we will call it, so now beta is a curve in the domain U, so it's given by a pair of functions, u of t, v of t. Okay? So in fact, you can take the proof of this proposition for the differential, and you can start writing in 10 minutes. I have to recover, because then, now I need to compute the second derivative, but you have already in your notes the first derivative. Okay? I have to do it again. Okay, so how do I write f of alpha, because this is my object here. Now with all these notations, f of alpha of t, I write it, of course, as f composed x. Remember the stupid trick. Composed x inverse composed alpha. And now x inverse composed alpha is beta. Okay, so this is, of course, at the point t. So this is f composed x of u of t, v of t. Okay, I'm just keeping on writing. And now we have to do the second derivative of this expression. Okay. I challenge myself. I didn't write it, so now it's going to be fun. Because of course, in order to compute the second derivative, we first need to compute the first derivative. And not compute it at t equal to 0. Because then we will have to take another one. Okay, so by chain rule, this is what? This is the derivative of this with respect to u times the derivative of u with respect to t, plus the derivative of this with respect to v times. Okay, so this is u prime. Now I drop the dependence on t. Everything is at the point either t or u of t, v of t. Okay, times f composed x u plus v prime f composed x v. Okay, now you have to start writing again. This was the end of the proof of the analog proposition for the differential. Now I have to take the second derivative, and I do it in the same way, chain rule. Okay? This, okay, so now second derivative. And now it is true, this one I only care about t equal to 0. But let's write down the whole thing, and then we put t equal to 0 to see if something helps. Okay? Okay, if I take, now this is a mess, of course, because I have to take first the derivative. I can take this is a product. This is a vector and this is a function. This is a scalar and this is a vector. So this becomes, of course, u double prime f composed x u plus plus u prime times the derivative of this. But this is again is a function of this type. So it has a u and v variable. So I better open a bracket. And this will become the derivative of this with respect to u times u prime. So this becomes u prime times f composed x u plus v prime f composed x u, which was there from the beginning, and now times v. Okay? Remember that these are computed at t and these are computed at beta of t. No? Okay, so this is that's for here. So of course this would be symmetric in u and v. So I don't have to waste too much mental energy. I just replace u and v here. So this is v, but it's better to write it well. V double prime f composed x v plus v prime times u prime f composed x vu plus v prime f composed x vv. It's not unlikely that I do mistakes, so correct me. It seems so correct. Okay. Now, how do I want to order it? Now, compute it. Now I add this symbol. At t equal to 0, well, not sure I want really to do it. Let's do it even. Let's write. I know. Let's write another. So this. Let's just group together because there are some things that we can put together. So I'm thinking of it as nothing. U prime, u double prime, f composed x u plus u prime squared So what is in u? Let's order with, so this takes care of the second derivative of u. Now there is a first derivative squared of u. Does it appear anywhere else? No, there is only one term, so this stays there. F composed x u. But then I have a u prime, v prime, and this, yes, should appear twice, no? So this is u prime, v prime, times what? This and this, so it's twice the same thing, actually. And now I've taken care of this, and I've already used this one, okay, in the second expression. So now if I want just to be symmetric in my Blackboard, I put v prime squared, no? This term here, which takes care of f vv, and now I'm left only with this, which is the symmetric of this, so plus v double prime f composed x v. Okay, so this is a formula which holds for any t. Now the question is, does it solve the problem? Which gives me 1 minute to recover.
When we substitute by t equal 0, yes.
Well, if you go back to the proof of the differential, actually substituting t equal to 0, also there I had to substitute t equal to 0, but actually it didn't make any difference. So now, so what is nice and what is wrong? I mean, the first claim is that it's well defined. It does not depend on alpha. So in some sense you can, I mean, you just have to be careful, because of course if you just look for alpha here you don't see it, but that would be the stupid answer. Of course you don't see it because you are seeing what? You are seeing the functions u of t, v of t. Alpha is there. Okay, so you don't tell me here there is no alpha. Okay, here there is no alpha. Alpha is here, here, here. It's in all these things. So of course it depends on alpha. In fact, the output should not be, it does not depend on alpha. It does not depend on alpha among all alphas which have something in common. And what? So now this is actually a good moment also to write for all these things, for all these partial derivatives. But let's write only for this one, for example, where it is actually computed. So this is computed at the point u of t, v of t, beta of t, if you want. So what is fixed in this story? P and V. Okay, what is V? I mean, what is P in this language? U of 0, V of 0. Okay. And what is V in this language? U prime 0, V prime 0, in the sense that this is, strictly speaking, would be beta prime of 0, but of course the knowledge of beta prime and V is the same thing. It's just you have to apply the differential of x to get one from the other, no? So the question is does this formula depend only on U of 0, V of 0, U prime of 0 and V prime of 0? That's the correct question. And the answer is clearly no. These two terms are undecidable by fixing these two things. If a curve has a tangent vector, you will never know how much is its acceleration. I mean, otherwise there would be an incredible theorem like every curve with given velocity has the same acceleration, which of course It's a
Do we have
monster.
an additional assumption?
So why the theorem is true? Actually, I wrote a theorem, so either I'm completely crazy after the pizza or what. I mean, the theorem is true because the coefficient of the bad terms are exactly the derivatives of the differential of f. I'm sorry, not the derivative. The components of the differential of f. So this is, so it's not this which vanishes, but it's actually this one which vanishes. So this at the point, and this holds only, so at t equal to 0, this vanishes and this vanishes. Okay? Now we are in good shape. Because now, yes, I can say what is left depends only on P and V. Okay? But because of this, that's why I will not be able to use this formula away from a critical point. It will not be well defined. Okay? Plus, okay, and as usual, remember we want to say, the differential is well defined, it's a linear map. And actually the proof was stopped here. No, I remember, usually at this point I do like this. And I'm doing it again. Why? This formula proof, once it's well defined, the only delicacy is here. Once it's well defined, everything here is automatic.
Because we can just take the curve and the right for the case of...
Well, first of all, why it's a quadratic form? What does it mean it's a quadratic form? Because how does it depend on the component of the vector? It depends exactly, it has a quadratic form. It's the first component square, no? It's the vector. You can write in matrix form, it's u prime, v prime, a matrix, u prime, v prime. And actually you even know which metric is it. It's the old Hessian. So in fact, again, it's all the same principle. What is the Hessian of a function on a surface? Well, it's that object that if I represent it in coordinates, is represented with respect to the standard basis by the old Hessian. So again, I'm transferring on a surface via the local chart the old definition of a domain of R2. This is what this formula is telling me. Okay? So it is a quadratic form. And why the calculus theorem is obviously true? I don't have to waste time. Well, precisely because what I just said. This is the Hessian, the old Hessian, or instead of the Hessian of f is actually represented with respect to the standard base, is the old Hessian of f composed x. But being a maximum and minimum, of course it does not depend if you compose it with x or not. So P is a maximum for f if and only if it's a maximum for f composed x. I mean, you're just changing parameters, but the map is the same. Okay? So all the theorems in calculus automatically pass to this. Okay? I really don't have to prove it. Very good. So this is slightly more delicate than all the others, no? Theorems of this type that we have seen. Okay, so also to conclude this lecture, so this is the new theoretical ingredient we will work on for a couple of lectures. Let's see just a couple of examples. And then we are done. Actually, for those of you who I've already noticed that many of the things that we are doing have nothing to do with dimension 2. Did you really care here about every time, maybe if somebody wants to have an exercise in mind, whatever I say, when are we really using that this is a domain of R2? In some things we did. But for example, here, in principle, I could be speaking of n-dimensional regular surfaces. And I would be able to define the differential, the Hessian, and so on. Okay? So we have a good list of geometrically interesting functions defined over surfaces for which we actually computed the differential. So let's see if for some of them we can compute the Hessian. I thought I forgot my notes, so okay. So examples. So one, let's go back to the height function. So remember what it was. This was a surface. You have a surface in R3. You fix a plane. Okay, we have our surface S. We have one plane P with some normal vector A. In fact, sooner or later we should, yeah. In fact, first thing, I think we did the computation in general, but let's normalize the normal vector to the plane to be of norm 1. Otherwise, it's just a waste of time. And let's say that this plane P here, this is a capital P. It's a plane. So I have to give you a plane, I have to give you a point and the vector. Okay, so suppose I give you P naught and A. I have this plane, I have my surface S. And remember which was the height function. So H was the function defined from S to R, which was taking P and was giving me the height of this point with respect to this plane. So remember it was, you take P minus P naught and you measure the oriented length of this vector. Okay? The oriented length means I take the scalar product. Okay? So this is H of P. Okay? So let's do the computation. How do I compute the Hessian? Well, of course, at a given point. Well, first of all, let's compute the differential, because I need to, first of all, to identify critical points. No? We did it already, but it takes a second. So, which is the differential of H at a given point P. This is d in dt, t equal to 0 of H composed alpha. So, of course, alpha goes here, and this becomes just derivative with respect at t equal to 0. This becomes V scalar A. Okay? Okay. So, this is the differential applied to the vector V. Differential applied to vector V means I take a curve alpha passing through P with direction V and blah, blah, blah. And that's the formula. So remember, I need to take a critical point in order to do the Hessian, but we have already interpreted the critical points equation. So what does it mean? It's a critical point, the differential is 0. How can it be 0? That the tangent space is orthogonal to A, because this has to be 0 for any V. Meaning, now you can phrase it in 1 million ways, no? Meaning, the tangent space at the point P is parallel to P. That's one way. Or, the normal line at the point P, what? Passes through P naught. Okay. No, or well, I mean, you can say, no, okay, it's like n at the point P is equal to A, for example. This is the critical point against another one. I mean, you can rephrase the same thing. It's always the same thing. It's like the tangent space is parallel to P, okay? Now we have to assume it. So for a point for which this happens, I compute the Hessian, okay? at the vector v. And then, of course, I need to take the second derivative of this. So I go back here. The first derivative was actually, here I've already substituted alpha prime of 0. But if I take just the first derivative at time t, this becomes alpha prime at t, scalar a. So if I take the second derivative, this becomes just alpha double prime at 0, scalar a. Okay, are you with me? So, but a, so this, in order for being so this is the critical point equation. Okay. One way to write the critical point equation. So this makes sense only at those points. So in particular, for those points, I can say that the Hessian is equal to alpha double prime 0 n of p. I really see the point p coming in, but we have already encountered this. What is the acceleration of a curve?
It's a curvature. Almost.
Which?
It's a curvature times the normal.
Which curvature?
Of the curve itself.
This is the normal curvature.
It's the normal curvature of alpha. Otherwise said, we proved Euler's theorem, which was saying that the normal curvature is equal to remember, it's the second fundamental form applied twice this vector v. Okay? But this is nice, and actually that's a nice way to conclude, because if, so what have we discovered here? We discovered that the second fundamental form, a new geometric interpretation of the second fundamental form, in the sense, well, it's almost an analytic interpretation, in the sense that the second fundamental form, we have seen, it's the same thing as the Hessian of a function. Okay? So it must satisfy, for example, remember what was in the blackboard here, the calculus theorems are now becoming geometric theorems. Okay? So these are now immediate corollaries of this computation. Under our usual conventions, no? H is the mean curvature, K is the Gauss curvature, and so on. So one, if K at P is positive, if you have a point where the Gauss curvature is positive, then there exists a neighborhood U, well, U maybe is not a very nice name, U. Maybe I don't have, let's call it V, a neighbor V of P in S, which lies on the same side of TPS. If K of P is negative, of course I could have said if P is elliptic or P is hyperbolic, I just don't want to use now the word. Then there exists a neighbor V of P in S, sorry, not that exists, for any neighborhood V of P in S, there are points on both sides of TPS. Okay. Exercise for you in the sense that you just have to convince yourself that I'm not cheating when I say there is nothing to prove. Just remember what? What is the Gauss curvature? Is the determinant. Okay? Plus the calculus theorem. If it's positive definite, then it's a minimum. If it's a negative definite, it's a maximum, blah, blah, blah. I'm just applying the calculus theorem to this. The only nice thing is you can say, well, but come on. This corollary is about any point with, okay, I put a property, but it's any point. While here, it seemed I had to do the computation of the Hessian for very special points. It's true, very special, because I first had to identify critical points, and then I could go on to Hessian. So your criticism could be, no, professor, because P, I start with an elliptic point. I have no idea whether P is a critical point for the height function for this plane. True. Except
So I can change
I can change the plane. I'm free to change the plane. So the claim is, give me any point. Any point is a critical point for the height function over some plane. And this is obvious. In fact, which plane? The tangent plane. There's only one plane around. Okay? So now, draw a picture, no? I mean, suppose you were working on your paraboloid, for example, no? And I want to prove, I take an elliptic point. Remember, actually, the paraboloid was actually made all of elliptic point. We computed the Gauss curvature. K was positive everywhere. But just to maximize, so I'm taking this point, I'm looking at the height function over its tangent plane, and this has to be a minimum. But now I'm working the other way now. I computed K. K is positive, this has to be a minimum, and this tells me the function, so this function has a minimum. But what does it mean? Actually, the minimum is actually 0. If you're computing the height over its tangent plane, the point P makes H equal to 0. No? So it lies on one side. What does it mean? So it lies on one side because it's a minimum. Okay? And so on. All these theorems. So that means this is very useful. Note that unfortunately, I underlined the unfortunate calculus theorem. So if it's positive definite, something happens. If it's negative definite, something happens. If it's semi-definite, you cannot conclude. So why there is no point 3 here? If K is equal to 0, now, okay, maybe next Thursday we will start with showing with examples. So for any conjecture you can make for K equal to 0, I will provide you an example which destroys the conjecture. There is no theorem, but actually it's a bit stupid in some sense. It's a nice way to have examples, so we do it. But it would be like saying, since this theorem is exactly the calculus theorem, it would be like saying there is a theorem for semi-definite Hessian that nobody told you because they are bad people. I mean, if there was a theorem here on surfaces, there would have been a theorem on calculus about functions where the Hessian is semi-definite. And there is none. You know, there you can take your calculus book, and I'm sure at that point there is an example for any conjecture. You say, if it's semi-definite, it's a local minimum. No, If then it's a local map, no. If whatever you think, it's no. So okay, here it's just the fact that this function is the height of, is geometrically meaningful. Okay, so there's nothing more than that. But this is extremely powerful in that at least just by watching a surface, I can tell you where there should be elliptic points and hyperbolic points. It's not an if and only if, but this tells me already quite a lot. I mean, this is a surface, no? I am a surface. I mean, you can look at me and say, ah, if my teacher has an elliptic point is here, here, well, I should have some hyperbolic points maybe here, so, and so on. I mean, no, it's extremely powerful just by looking at the picture of a surface. So you can guess where positive curvature is, negative curvature is. Okay, you will never be able to guess where zero curvature is. Okay.